In this video, we'll talk about direct map caches. These can be contrasted to associative caches, and when we talk about the general case later on, we'll see that the general case is a combination of both associative caching and direct map caching. With associative memories, there is an unfortunate design trade-off. We can either build the memory to be small, or we can make it larger, but then it's slower. The fundamental problem is that all the lines in the associative memory have to be matching at once, so we have to broadcast the key to all parts of the memory, and that takes more time and more power. So associative memories are not practical at larger sizes. So there's another approach which is called direct map cache, and these caches do not use associative memory principles. So let's start by looking at an example of a direct map cache. We'll stick with our block size of 64 bytes, and in this cache we'll have 512 lines. So if we multiply these together, we see that the cache size is 32 kilobytes. In a fully associative cache, any block can go into any cache line. Okay, it's associative. It doesn't matter where you put it. With a direct map cache, each block can only go into one particular cache line. So a given block, for example, block number 514, can only go into line 2. Okay, it can't be stored in any other line. And likewise, line 2 can only hold certain blocks. It might hold block number 2, or it might hold block number 514, or it might hold block 1026, and there could be many other possible blocks that could go into line 2. But each block in main memory can only be put into one particular line. For example, block 512 might go into line 0, block 513 might go into line 1, and block 514 can only go into line 2. So just as with a fully associative cache, each line still needs to contain information about which block is currently being stored in that line. But with the direct map cache, we now can avoid the associative lookup. If we are looking for a particular block, well, it can only be in one possible line, so there's only one place to look for it. All we have to do to retrieve a particular block is retrieve the line that it has to be stored in, and then check to see whether that line really did in fact contain the right block. So we're going to look at a cache with 512 lines as an example, and note that 2 to the 9th is 512. So we can address any line in the block with a 9-bit number. So here's how the direct map cache system works. First of all, let's look at our address. It's 32 bits, and as before, the last 6 bits will be used to choose the byte from within the block. Each block has 64 bytes, so it takes 6 bits to pick out the byte of interest. But here's where it differs. We're using these 9 bits as an index, and the remaining 17 bits are a tag. So the direct map cache will store not only the data for the block, but it will also store the tag. So each line has not only the 64 bytes here, but it also has 17 bits for the tag. There may be some other bits for valid and dirty and so on, but these aren't shown here. And so when the cache is presented with a 32-bit address, what does it do? It pulls off the 6 bits for the block offset, and then it extracts the 9 bits here and uses those as an index into a normal sort of memory. So this is a normal sort of memory where every line has its own address, and these sorts of memories are fast. This is just like a normal DRAM, except instead of having only 1 byte for each address, you've got a bunch of bits. You've got 64 bytes here and 17 additional bits here. But other than that, it's a typical sort of DRAM style memory. So the 9-bit index is used to select one particular line, and then that line is retrieved, and in the second step we match the tag from that line to the tag that we're looking for. And if they match, we know we've found the right block. If they match, we know that that block was in cache, and so we are in luck, and the cache can return that data to the CPU. It can use the block offset to extract the appropriate byte and then send that byte back to the CPU. So to repeat how the direct map cache works, the cache receives an address from the CPU, and from that 32-bit address it extracts the tag, the index, and the offset. And then the cache uses the index, in our example it's 9 bits, and it uses it as an address into the cache memory, and it retrieves the entire line from the cache. Then the cache compares the tag bits, in our example it was 17 bits, and it compares that to the tag that was stored in the line that got retrieved. And if they are the same, then we know it is a cache hit. And if the tag is different, then we know it's a cache miss. And finally, if it's a cache hit, then in the final step, the individual byte or bytes from the block are extracted. So the cache uses the offset, the remaining 6 bits of the address, to determine which byte is wanted, and then it extracts that byte and returns that byte to the CPU. Let's continue with our example where we're using a cache that has 512 lines. So over on the right-hand side, I'm depicting main memory, and every chunk of 64 bytes is a block of main memory. And so the idea is that there's 64 bytes here, there's another 64 bytes here, and then there's 64 bytes in each one of these chunks. And memory, all 2 gigabytes of it, all 4 gigabytes. It's a 32-bit address, so we have 4 gigabytes of memory. All 4 gigabytes of memory is divided into blocks. If a block is in cache, then, well, this is a direct map cache, so that block can only be stored in one particular line. Okay, so if the block is in the cache, it will be in a particular line. For example, if block 3 is in the cache, it will be in this line here. And so over here I've shown for each one of the lines of the cache which blocks might be stored in that line. At any one point in time, the line can only contain one of those blocks. It can only contain 64 bytes, and it will either contain one block or some other block. So the first line, which we call line 0, can contain this block. Line number 1 can contain block number 1. Line number 2 can contain block number 2, and so on, all the way up to 511, and then block 512 has to go into line 0. So line 0 can either store this block or block 1024, which is down here below. And there are many, many blocks in our 4 gigabyte memory, and so there are many, many possible blocks that might be stored in line 0. But as you see, each block can only go into one line, and that tells you exactly where to look for it. So, for example, if we're looking for block 514, we look in line number 2, and it's either there or it's not. So that's what the tag bits are for. Now, what can go wrong with this system? Well, notice that this particular line, line number 2, can either contain block number 2 or block number 514, or block 1026, and so on. So block 2 and block 514 happen to be mapping to the same line. If they are in the cache, then they will be in this particular line. So only one of these blocks can be in memory at the very same time. Okay? Blocks 2 and 514 must be placed into the same cache line. Now, here's the problem. What if our working set happens to contain bytes in both blocks? Let's say it contains a byte here, down at the bottom of block 2, and maybe the working set also contains some bytes at the beginning of block 514. It's not too likely, but it's possible that when we're executing a particular section of the program, we need information from block 2 and we need information from block 514. This is a conflict. We can only get one of these blocks into the cache. So if our program is executing and it wants to use this byte, then it will load this block into the cache. And then very soon thereafter, it might need this byte. So it evicts block 2 and moves block 514 into the same spot. And then it accesses this. And then perhaps it needs to go back and access this byte again. Well, it'll have to evict 514 and move block 2 back into the cache. So you can see what's going on. It can't keep both these blocks in the cache at once, and if both blocks contain data that's part of the working set, we've got a problem, and that problem is called thrashing. So in this particular example, there's a conflict, and the cache thrashes. And this is not too likely, but it can really occur, and when it does occur, it's going to just really affect performance in a very negative way. So we can't really tolerate cache thrashing, and so this is why direct mapped caches by themselves, as I've described them, aren't quite adequate. But it's a starting point, and we'll move on to the general case in just a second and see how we can solve that problem. But before we move on, let's look at what's going on here in a little bit more detail. The 32-bit address is broken up into 17 bits of the tag, 9 bits of the index, and then 6 bits to select the byte within the block. And in all these addresses here, the index is 2. Binary 10 is equal to 2. So all of these addresses will map into line 2 of the cache. We don't really care what the offset bits are, because those are whatever they are. All addresses that start with these 17 and 9 bits, in other words, that start with these 26 bits, any address that starts with these 26 bits will map into line 2 of the cache. And so these are coming out of the second block in main memory. Okay, 10 is 2. And as we change the tag values, if you look at this in binary, the number 10000000010 is 514, and this number 10000000010 is 10,026, and so on. So you can see that the high order 26 bits give the block number. Okay, and so all of these blocks, block 2, block 514, block 1026, all map into line 2 of the cache. So any byte that has an address of any of these forms will go into cache line number 2. Now we're ready to look at the general approach to cache design. We're going to combine the best features of the associative caches with the best features of a direct map cache. So in the general approach, we combine the best features of the set associative caches with the best features of the direct map caches. And to illustrate this design, we're going to look at a specific example, and it will be a 32 kilobyte cache that's 8-way set associative. So the idea is that we have a lot of little associative memories. We have many small associative memories, and each one of these associative memories is quite small. And in this example, because it's A-way, each one has only 8 lines. So the block size is 64, we can call that B. The number of lines in each set is small, in this case it's 8, and we'll have 64 sets total. And this gives us our total cache size of 32 kilobytes. Here's how it works. We've got a 32-bit address, just as before, and we're going to divide it into a tag and an index and the block offset. So this is just the same as we did before. The tag will now be 20 bits, and the index will be 6 bits. That's the only difference. The block offset will remain at 6 bits. With 6 bits, we can address any byte within the block of 64 bytes. And as I said, we have 64 sets in this particular example. So with 6 bits of an index, we can choose which associative set we want. And then the remaining bits form the tag. So we can use this picture to show what this thing looks like. Okay? I suppose I could draw a box around the whole thing, but this is the cache memory. Each line has both the tag and the 64 bytes of data, just as before. But it's divided into sets, and we've got 64 sets total. And each set has 8 lines, 1, 2, 3, 4, 5, 6, 7, 8. So we have 64 sets, 8 lines each. So how does it work? Well, the cache is given a 32-bit address. It starts by extracting the index, and that identifies which set is involved. So the first step is to extract those bits and identify the set, and that set is then the one that we look into. So the cache, it's an associative set, so we provide the tag to that associative set, and that associative set then checks all 8 of its lines to see if there's a match with a line that's already in the set. And if there's a match, then we've got a cache hit. So now blocks 2 and 514, for example, remember they mapped to the same line in the direct map cache, but now what happens? Well, they both map to set 2. Okay, so that's just as before. So they both map to the same set. But set 2 is more than just a single line. It can hold up to 8 blocks. So the direct map version, blocks 2 and 514 mapped to line 2, and it could only hold 1 block. But now these same 2 blocks map to the same set. However, the set can contain up to 8 blocks. The set is associative. So now the conflicts are much less likely. Okay, we can still have conflicts, but it's much less likely. So going back to the previous diagram I had before, here is block number 2, here is block 514, and there may be some bytes that are in block 2 that are important, and there may be some bytes that are in block 514 that are in our working set. But both these blocks can be kept in the cache at the same time, because we can put each one of them into set number 2, and each set can contain up to 8 blocks. It will contain 8 blocks. So in this case, we're able to avoid that sort of conflict. And this is the sort of design that is used in caches. In this video, we'll talk about the different kinds of cache misses, and we'll also talk about what can go wrong in particular pathological cases. A cache miss occurs when the CPU wants a piece of data, and that data is not in the cache. And what are the reasons for the miss? Well, there are really three different kinds of cache misses: compulsory, capacity, and conflict misses. So the first kind, the compulsory miss, occurs when the program first begins. Obviously, when a program first begins, its data, its working set data, is not going to be in the cache. So the first time the data is accessed, there will be a cache miss. And you have to load the cache, and so that's why we call it a compulsory miss. Sometimes we talk about the cache being cold. The idea there is that when the program first begins, there's nothing in the cache. The working set is not yet in the cache at all. So the cache is cold, and in the first part of the program, as the program gets going, it will load its working set into cache, and after that we say the cache is warmed up. For some computers, the cache might be just too small to contain the entire working set. And if the cache is too small, then we can't get the entire working set into the cache, and so we're going to have misses as a result of that. And those are called capacity misses. The idea is that if you could make the cache a little bit larger, those misses would not be happening. And finally, we have a conflict miss. Here the idea is you've got plenty of room in the cache, but there are two blocks in the working set that happen to map into the same part of the cache so that they cannot both be in the cache at the same time. So even though there's plenty of room in other parts of the cache, because of the way the cache mapping occurs, there's a conflict miss. We saw how this could occur with a direct mapped cache, and the solution is essentially to have a set associative cache. And so with an 8-way set associative cache, you have each place in the cache containing an associative memory, so you can put 8 different things in there. So the conflict misses go way down with modern cache design. So if we do have misses, then things can go bad. And one thing that can go bad is, look at this situation here. Imagine that both blocks X and Y are in the working set, and somehow they map to the same place, or for some reason when we load X we end up evicting Y, and then because they're both in the working set, pretty soon we need Y, and when we load Y we evict X, and then pretty soon again we need X once more, and so we load X evicting Y, and this process goes on and on. So we've got a very serious situation, and that situation is called thrashing. Suddenly every access is a cache miss, and performance is going to fall dramatically. Cache thrashing is very bad. We might as well not even have a cache. So if this occurs, we've got a very bad performance problem. Let's take a look at a program which might be typical of what you might see. These lines up here indicate instructions and code, and the idea is that you've got a loop. So these instructions here are executed repeatedly over and over. And maybe in the middle of the loop we call a subroutine, and that's indicated by this code over here. So we jump over here for a moment, and then we return to the loop, keep going, and maybe we call another subroutine. So in this particular example, this loop does a bunch of stuff, and that includes calling these two subroutines. We might have more subroutines. Maybe this one calls yet another one, or perhaps this one calls this one as well. But in this particular example, I think we've got a pretty tight loop, and we've reduced procedure calls from the loop body as much as we can, and there still are 2 procedures called, which is probably something to think about if you're worried about performance. But let's say this is a typical unoptimized program. And what does this program do? It accesses some data. So it may have some static data variables, accumulators, sums, and so on. So those variables are indicated with these lines here. So here's some data, some variables that get accessed. This loop may be going through some arrays. After all, if we're worried about performance, we're executing this loop a whole bunch of times, and that means we're probably doing it on arrays. So maybe we're accessing some array A and some other array B. We may be coming back to X, Y, and Z over and over and over again, whereas with these arrays we're sort of stepping through them sequentially, or jumping around. If we have a stride 1 program, if our program is exhibiting stride 1 behavior, then it's going through memory sequentially for the array. And we would hope that it's behaving with stride 1 access patterns for both these arrays. Okay, so we've got 1, 2, 3, 4, 5, 6 hotspots. And those hotspots are somewhere in memory. And here I'm just suggesting that one hotspot's here, there, and we've got 6 hotspots in memory. The instructions in those hotspots are going to get mapped into cache, into blocks. So the red circles here indicate a block of data. In our example, using the size of the caches for the Intel chips, the block size was 64 bytes. So these red circles are circling 64 bytes at a time. And you see a couple of different things going on. In the case of variables XYZ, maybe the entire hotspot fits into one block. Let's see if these were lined up. Maybe it's this subroutine that's fitting into one block. On the other hand, the hotspot might happen to be on a block boundary. So even though maybe you have only just a few bytes for X, Y, and Z, they may have, by unfortunate chance, been positioned so that a block boundary is crossed. With the arrays A and B, we're probably going through them sequentially. So here I'm showing that at one moment in time we're sort of working on these elements of one array. And here I'm showing that the array may be very big, but at one instance of time we're going through these elements. And later on the working set will shift and the next block will be needed. Now, how many blocks are we looking at here? Well, in the worst case, all of these blocks might map to the very same set. Okay, but notice when we have two adjacent blocks that they will not map to the same set. So they will map to different sets. This one will map to perhaps set 2 and this one to set 3. So here we have 6 hotspots. Okay, so we might be mapping this one to the same set as we're mapping this block, and maybe this block happens to go into that set, and this one, and this one, and this one as well. Well, the adjacent blocks, this block and perhaps the block above it, will go into different sets. So with an 8-way set associative cache, it's not a problem. We can get this block, this block, this block, this block, and this block, and this block. That's only 6 blocks into the set and still have 2 lines still available. So what is our worst case scenario? Well, maybe the working set is really, really large. In the previous example, I showed a working set that had 6 hotspots, but maybe we have more hotspots. And maybe they all happen to map into the same set. Well, that would be a problem because each set has only 8 slots. But we have 64 sets total. So for the chance of all 10 of these mapping into the same set is pretty low. So this is not really that much of a concern. Some hotspots may require several blocks, like we may have a particularly large loop, and I've shown this over here. So this hotspot requires lots and lots of blocks. But notice that the adjacent blocks go into different sets. So this block here might go into set number 7. Well, that means this one goes into set number 8, this one goes into set number 9, and 6 and 5 for these 2 blocks. So they're going into different sets, so we should have no problem there. Some hotspots can be very large. The block size is 64 bytes, and we've got a total of 64 different sets. So the hotspot would have to be greater than 4 kilobytes in order for some set to contain more than one block. from that same hotspot. In other words, it's got to be really pretty big. There's 4 kilobytes between this block and this block, and if the hotspot is really that big, then eventually we'll have to put another block from the same hotspot into that set. But that's a very unusual hotspot. It's so big that we're sort of stretching our notion of the working set to start with. But if that did occur, well, it's still not really much of a problem, because keep in mind each set can contain up to 8 lines. So we can get both these 2 blocks into the cache at the same time. There's another kind of problem we might want to consider. We have made the assumption up until now that the principle of locality applies to our programs. But what about programs that don't have locality? They jump all over the place. Sometimes this is called spaghetti code, and here I've tried to show you that this program has really chaotic behavior. It's jumping all over memory, and you can see why they call programs that are coded in this way spaghetti code. What's going to create a program that has this behavior, this lack of locality behavior? Well, it's kind of hard to imagine, but maybe some sort of a neural net simulation where you're jumping all over memory to follow the neural connections. It's hard to really imagine programmers doing this. Programmers write pretty organized code. Maybe a few beginning students use go-tos more than they ought to, but even though they do use go-tos instead of structured programming concepts, the resulting programs still exhibit the locality that we're talking about. It's kind of hard for programmers, human programmers, to create code that's really chaotic. It just is not something that happens. But maybe there is some code that's being generated automatically by some software. I suppose it's conceivable that it could be generating code that does not have locality. There may be some algorithms, some very unusual algorithms that really jump around a lot, and these may not exhibit the locality that makes caching work so well. In particular, if you have graph-like data structures, then they may jump around. They may have all kinds of links that go from one point in memory to the next point in memory. Here I've shown object-oriented programming. These little rectangles here represent objects, and each object contains references or pointers to other objects. And the programmer may see some organization to these things, but where they go in memory is really an artifact of what memory happened to look like, what was free when the objects were created. So usually there are patterns to the way programs work, and these things end up more or less going close to each other in memory. But maybe not. Maybe they're added willy-nilly, bit by bit. You're building up this graph in odd ways, and so these objects are located far apart. Well, any algorithm that works on a data structure that looks like this is going to jump around a bit. Also, with garbage collection and object-oriented programming, the objects don't necessarily have to be near each other, and so it may be that the objects get moved around during garbage collection, and there's no particular need to keep them close to each other. So they may drift around in memory over time and end up being located in more or less random places. But nevertheless, most programs do exhibit locality of reference, and so this principle of locality means that programs do have working sets, and so the whole concept of cache works. We can most always get the working set into cache, and so the program runs faster. I'd like to wrap up this video series with a review of some of the main concepts that we've seen so far. Generally speaking, cache memory is about maybe 10 times faster than main memory. Cache is made out of static RAM, and main memory is made out of dynamic RAM. If we can get the data that the program needs into cache, then when the CPU wants that data, there's a cache hit. The data that we want is in the cache memory. If the data that the CPU needs is not in the cache, then that's a cache miss. And we saw that there are several different reasons. It might be a compulsory miss. The cache might be cold, and if the cache hasn't been warmed up yet, then the working set is not in the cache, so there is going to be a miss for sure. If the data in the memory, in the cache, is in a location that conflicts with some other data in the working set, that means you can't get both of those pieces of data into the cache at the same time. And so there's going to be a conflict, and if one piece of data is in the cache, then the other one won't be. So you'll get a miss, and that's a conflict miss. And it also may be that your cache is just too small to contain the entire working set. So that will cause misses that are called capacity misses. The computer moves data back and forth between main memory and the cache memory in units called blocks. And we looked at examples where the block size was 64 bytes. The cache is made up of a number of lines. Each line in the cache stores one block. In addition, the line stores some more information, such as a tag to indicate which block it is. It may also store a valid bit or a dirty bit, and perhaps some other information as well. So the line is bigger than the block because the line contains a block of data as well as tag and other information. When we talk about the size of caches, we talk about the amount of block data that's in the cache. The tags and other bits are not included. We talked about associative memories in general, and we saw how we could use an associative memory to build a fully associative cache. That's not ideal, but that was our first step at looking at caches. And then we looked at a different approach, which was direct mapped cache, where we used some of the bits in the middle of the address to form an index. And then we went into a normal addressable memory and found the cache line that way. And then we combined these two techniques, the set associative memory with the direct mapped cache, and created the kind of cache that we see used in practice today. When there is a write to the cache, what do? Well, we looked at a couple of different approaches. If the data is in the cache, then we could write it and update the version that's in the cache and immediately send the write on through to the main memory. This is called write through. Or we could just update the copy of the data that's in the cache and not update the memory just yet. And only later, when the block is evicted, do we write the block back to memory. And that's the write back strategy. If we perform a write to a block that is not in the cache, in other words, if we have a cache miss during a write operation, we have two approaches, and one is to allocate a new line in the cache memory and read the block in and then update it there. Or we could simply update the main memory and not allocate a cache line at all. And that's the write with no allocate. We talked a little bit about hit rate and miss rate. Whenever we have a hit, that's good, of course, and whenever we have miss, that's bad. And each access to the cache is either a hit rate, is either a cache hit or a cache miss. So these two sum to 100%. We talked about the principle of locality. Programs tend to use the same pieces of memory over and over again. And so most programs exhibit locality. We talked about different ways they can be exhibiting this principle. We have spatial locality and temporal locality. The idea with spatial locality is that if a particular byte of memory is accessed, it's likely that nearby bytes will be accessed in the near future. With temporal locality, the idea is that if one byte of main memory is accessed, there's a high probability that that same byte will be accessed again soon. We talked about the working set. When a program is running in a particular section of its execution, it's going to need some instructions and some data in memory in order to execute. It may not need the entire program instructions. It may not need all of the instructions. It may not need all of the data, but there's this concept that over a short duration, over a short interval of the program's execution, some things are needed, some bytes are needed, and other bytes are not. And if we can get the working set into cache, then the access to those bytes that we need will be fast. If, on the other hand, we cannot get the working set into the cache memory, then the program will have to go out to the main memory. So the program will run more slowly because the CPU will not be able to get the data out of cache. It will have to go to main memory and pay a miss penalty for many of the accesses. So if there's a hit, that's good. But if there's not, if there's a cache miss, then the cache will forward the request to the main memory, which is slower. And so a penalty is paid, a time penalty is paid. We talked about how you can take, how the cache will take the address that's provided from the CPU and it will divide it into pieces. The tag, the index, and the offset. And we looked at an example where we had 64-byte blocks, so the offset was 6 bits. We looked at a situation where we had 64 different sets. So we had, again, 6 bits for the index, and that left 17 bits. You know, I never mentioned it, but in my example, we used 64 bytes for the block and an offset of 6 bits, and we used 64 sets with an index of 6 bits. Those two are the same, but that was just coincidence. That they're not necessarily going to be the same. So perhaps it's a bit confusing, but the number of bits for the offset doesn't necessarily have to be the same as the number of bits used for the index. And the number of bytes in the block is not necessarily going to be the number of sets. It's just a coincidence they were both 64. The cache line, in addition to containing the block of data and the tag to tell which block that is, will also contain a couple of bits. The valid bit and the dirty bit are two important bits that are in each cache line. When the computer's turned on, when the cache first powers up, we need some way to indicate that the bits that are in it are not valid, they're no good. And we do that with the valid bit. So by clearing the valid bit, we indicate that the cache line is effectively empty and unused. The valid bit is also used when we switch from one task or one thread to another task or another thread. Different processes have different address spaces, so what is in the cache for one process may not be the right stuff. It probably will not be the right stuff for some other process. So when the operating system switches from one process to another process, it's also switching from one address space to another address space. And so it will typically clear the valid bits for the cache, which effectively empties the cache out. The dirty bit indicates whether the block in the cache has been modified. And so if we have a write-back scheme where we're keeping the modified data in the cache without writing it through to the main memory immediately, then we need to keep track of the fact that the block has been modified. And the dirty bit does this. The dirty bit is set to indicate that the data in the block has been modified in some way or another. And we talked about programs that go through memory, and in particular programs that go through arrays. If they go through memory sequentially, they probably will have better cache performance. So we called that a stride 1 access pattern. So it's going through every byte in order. If it's skipping over bytes, say it reads 1 byte and then it skips 20 more bytes before it looks, then it has a stride 20. So these programs may incur a greater miss rate. And we also talked about thrashing, which might occur in some pathological programs or in some systems where the cache is not large enough or not well designed. And with cache thrashing, you have a very high miss rate. Effectively, every cache access is a miss. So the system spends all of its time evicting and reloading cache blocks. So thrashing is not good. What are the benefits of having a system with cache memory? Well, the main benefit is that we keep the working set for a program in the cache memory. The cache memory is faster than the main memory. And how much faster? Well, just as a rule of thumb or sort of a guesstimate, I put down 10 times faster. So caches speed the computer up by keeping the working set in a faster memory. We'd like to have, it's too bad we can't make the entire main memory this fast, but faster memory is more expensive. And the larger memory that is the main memory is going to be slower. One nice thing about cache is that it requires no special effort by the programmers. It is used for any program that runs. Cache is always used without any additional effort. And so therefore it's helping all programs. And so that's a nice aspect to it. Another good thing about having a system with cache memory is that when data is transferred from the main memory, it goes to the cache and it is transferred in block-sized units. So if our block is 64 bytes, we transfer 64 bytes from the main memory to the cache memory all at once. And since we're transferring so much memory at once, that transfer can be done more efficiently. In a computer with cache memory, the main memory basically is organized as a group of 64-byte chunks. So effectively the word size of the memory, the main memory, is now 64 bytes. We're kind of used to thinking of the word size of a memory as being 1 byte. In other words, each byte is separately addressable and we can read and write individual bytes. Well, that's slow. It's much faster to read larger chunks all at once because it can be done in parallel. So when we go to main memory to get a block of bytes, we're getting 64 bytes, and those 64 bytes may be spread across many, many different RAM chips. So by using many chips in parallel, we're effectively speeding up the bandwidth for the moving data to the computer from the main memory. There are also benefits to understanding how cache works. If you have code that is performance critical, then you want to optimize it somehow. And knowing how cache works is going to allow you to write cache-friendly code. Now, knowing what you've learned in this video series, you can optimize or structure your program to be cache-friendly and use the cache well, and thereby achieve significant performance improvements. Thanks for watching. Bye-bye.